Welcome back to the deep dive. We have a massive stack of notes and case studies on the desk today.
A truly intimidating stack, honestly.
Yeah, it really is. And we are aiming this directly at the project managers, the data leads, and, frankly, anyone who wants to pass that CPMAI certification.
Which is not an easy hurdle, by the way.
No, definitely not. So today, we are tackling the Phase 2 data understanding exam prep. And right off the bat, before you roll your eyes and think, oh, great, an hour on spreadsheets and column headers.
Which is what everyone thinks when they hear data understanding.
Right. But I want you to stop and really listen to what we're about to tell you. Phase 2 is the silent killer.
It absolutely is. I mean, it is the assassin in the room that nobody sees until the body drops.
That's a pretty dark image to start with.
But looking at the failure rates we see in the industry, it is entirely accurate. Phase 2 is where AI projects die. But the weird thing is, the death certificate isn't actually signed until months later.
Because the data looks fine at first glance, right?
Exactly. The data looks fine. The team is moving at light speed. Everyone is, high-fiving in the daily stand-up because the ingestion script worked perfectly.
But then, 3 phases later, like when you're in Phase V evaluation, or worse, when you're fully deployed in Phase Z script production, the whole model just collapses.
It starts hallucinating. It starts throwing wild bias errors. It completely fails to predict anything useful.
And when you do the autopsy on that project, you realize the poison was swallowed right here in Phase 2.
That is the perfect way to frame it. Because Phase 2, data understanding, isn't just about opening a CSV file and looking at the rows. It's about deeply, fundamentally understanding the raw material you are using to build intelligence.
And if that understanding is flawed,
then the intelligence is flawed. I mean, you can have the absolute best algorithm in the world, the most expensive GPUs money can buy, but if you don't understand the data, you are basically building a Ferrari with an engine made out of plywood.
It'll look great right up until you turn the key. And I think the silent killer label is so accurate because the code will still run.
Oh, it will compile perfectly.
Right. The model will still train. The math still works. It just won't work in the real world. So our mission for this deep dive today is to trace every single one of those downstream failures back to its root cause in Phase 2.
And we're going to do this a bit differently today, aren't we?
We are. We're going to run this as a simulation.
Yeah.
I am going to play the role of the exam coach. I've got the actual scenarios from the Phase 2 question bank right here in front of me.
And I will be the battle-hardened AI project manager who has the scars to prove all of this.
Perfect. So I'll pose the scenarios
and
you explain the why and the how, because we aren't just looking for, whether the answer is A, B, or C.
Right. We're looking for the underlying logic, the methodology that separates a pass from a fail on the exam, and frankly, a successful career from a very public firing.
High stakes. I like it. So here's how it works for you listening right now. I am going to pose a scenario. I'll give you 2 or maybe 3 options. Then I am going to say, take a moment.
And that is your cue. Do not wait for us to just spoon feed you the answer.
Right. Lock in your answer in your own head. Commit to it. And then we will reveal the truth and unpack the exact failure mode.
And keep your eyes open for the traps. Because the CPMAI exam loves, and I mean absolutely loves, to give you an answer that sounds logically correct in the real world, but is technically wrong within the specific phase methodology.
Yeah, they love testing those specific boundaries.
Yeah.
We need to highlight those distinctions today.
Absolutely.
So we have a roadmap covering 3 distinct task groups for this deep dive. First up is collect initial data. That's the foundation and the sequence.
Second is data quality, the ultimate gatekeeper.
And finally, machine learning modern data requirements. Those are the specific constraints for the AI itself.
Let's get to work.
Let's do it. We are starting with task group 1, which is collect initial data. And just to set the stage, this is classified as a high priority group on the exam.
Structurally, you really need to imprint this on your brain. This group contains 3 tasks that must happen in a strict linear sequence. You cannot jazz improvise this order.
It goes collect, then describe, then explore.
Collect, describe, explore. If you mix those up on the test, you fail the section. It's that simple.
So let's test your ability to spot the very first one in that sequence. Challenge number 1. We'll call this one the raw collection.
Set the scene for us.
All right, imagine a large financial services company. They have just greenlit Phase 2 for a massive AI fraud detection project. The project manager is coordinating an effort to bring together transaction records for the old mainframe, customer profile data from their CRM, and historical fraud case logs from the security team.
So 3 very different internal systems.
Exactly. The PM catalogs all of this with source system references, gets the necessary IT permissions, and makes all those files available to the project team on a secure server. That is the situation.
Okay. Focus on the action verbs in that scenario. Coordinating, bringing together, making available.
So the question for you listening is, which Phase 2 task has the project manager just completed? Option A, describe data. Or option B, collect initial data.
Think about what hasn't happened yet in that room.
Take a moment.
Yeah.
All right, the answer is B, collect initial data.
This is the foundational step, and the strict definition here is crucial because people tend to overthink it. This task is purely about gathering and making available the raw material.
Right, notice what did not happen in that scenario I read. They didn't analyze the quality of those mainframe logs.
They didn't write a report on the date ranges in the CRM. They didn't check for missing values or nulls.
They just went out, got the boxes of data, cataloged what was written on the outside of the boxes, and put them in a secure room.
That distinction is the key to passing this question, because option A, describe data, is the trap.
It is a huge trap. Because in the real world, as a data scientist, you might grab a file and immediately pop it open to see what's inside.
Of course you would. But in the CPMAI methodology, those are distinct, separate steps. It is the fundamental difference between logistics and analysis.
Logistics versus analysis. I like that.
Collect initial data is just the logistics. I have acquired the asset. Describe data is the beginning of the analysis. If you selected describe data for this scenario, you jumped the gun. You assumed the team looked inside the box, but the scenario only said they moved the box.
And this seems simple, almost overly semantic, but getting this wrong sets a really bad precedent for the rest of the project.
Exactly. If you think you have described the data just because you successfully downloaded it to a server, you are completely skipping the documentation step.
Which means you haven't established any kind of baseline yet. You just have a pile of files.
Precisely. So we have the boxes in the room, we have the access permissions, now we move to the actual second step in the sequence.
Right. Challenge number 2. Let's call this one the static snapshot.
This is where the formal documentation starts.
Okay, here's the scenario. The team is working on an AI demand forecasting initiative. Following that initial collection we just talked about, they sit down and produce a structured document.
A formal document?
Yes. And this document covers the originating source systems, the file formats, whether it's CSVs, Parquet, JSON, files that date ranges covered by the data, the update frequency, and the key attributes in each table. Crucially, this document is formally reviewed and signed off by the stakeholders before any data preparation planning begins.
Okay, look closely at the output there. A structured document, signed off, key attributes are listed.
So which task is this? Option A, collect initial data. Or option B, describe data.
Watch out for the nuances here.
Take a moment.
Yeah.
The answer is B, describe data.
Now, did you get caught thinking this might be exploration?
A lot of smart people do.
They really do, because listing key attributes sounds a lot like exploring. It feels active.
It feels like you are investigating the data.
Yeah.
You are looking at the date ranges, you're parsing out the formats.
But here's the memory hook you need for the exam. Description is a snapshot. It documents, it does not investigate behavior.
That's a great distinction.
This scenario explicitly describes producing a structured document covering formats and ranges. That is a static reference artifact. Think of it like a map of the territory rather than a geological survey of the soil.
It says this file contains integers, not these integers are highly correlated with our Q4 sales.
Exactly. Described data is just the facts. But why is this formal task so incredibly important? Why can't we just jump straight into the deep analytical exploration?
Because of the assumed knowledge failure mode.
Yes. This is the classic bus factor issue in data science. Imagine you have 2 engineers on your team, Alice and Bob.
Okay, Allison Bob.
Alice looks at the raw data and assumes the date format in the file is day, month, year, because she happens to be based in London.
Oh, I see where this is going.
Bob assumes it's month, day, year because he's sitting in New York.
And neither of them talks to each other about it.
Right. Without this described data document that explicitly, formally defines the format for the whole team, they both go off and build their preparation pipelines on entirely conflicting assumptions.
And then everything breaks downstream in phase 3 when they try to merge their prep code.
Complete disaster. The result is that the data preparation is done on incompatible foundations. You need that signed-off description document to definitively say, this is what the data is.
It prevents that chaotic, oh, I thought you knew moment 3 weeks later.
Exactly. It forces the team to agree on the basic, boring facts of the data set before they start manipulating a single row of it.
So it's essentially about forcing consensus on the facts.
It is the terms of reference for the data itself.
Okay, so describe data is what the data is. It's static. Let's move to the third and final step in this sequence. Challenge number 3, the cognitive investigation.
This is where it gets really interesting, because this is the step that is uniquely critical to AI projects. You don't typically do this in standard software engineering.
All right, scenario time. An NLP project team, so natural language processing. They are building an AI system to classify customer support intents.
A very common use case.
They examine the text logs for vocabulary distribution and coverage gaps. But crucially, they determine that the model needs annotated intent labels for all the query types, and that the data must represent the full range of user queries, meaning they need angry users, happy users, confused users.
Listen to that second part very carefully. Determines the model needs annotated intent labels.
So the question is this option A, describe data, or option B, explore data and cognitive data requirements?
Don't rush this one. Think about what they are actively figuring out.
Take a moment. The answer is option B, explore data and cognitive data requirements.
Honestly, the title gives it away. If you pay attention to the full formal name of the pass, it is not just explore data, it is explore data and cognitive data requirements.
Let's unpack that two-part nature, because this seems to be where a lot of test takers get tripped up.
It's two distinct jobs under one umbrella. Part 1 is the statistical investigation. That is the vocabulary distribution part of the scenario. You're running the numbers, looking at the spread.
Which kind of looks a bit like description at first glance.
It does, but it's deeper. It's truly analytical. You are looking at the content's behavior, not just the file format. You aren't just saying, this is a text string. You are saying, this text contains these specific words with this frequency distribution.
But part 2 is the real game changer for AI.
Part 2 is cognitive data requirements. This is where you physically stop asking, what data do I have? Yeah. And you start asking, what does the AI actually need to learn?
And in this specific case, it needed those annotated intent labels.
Exactly. Think about it. A spreadsheet doesn't need labels just to exist. A standard relational database doesn't need intent labels to function properly.
Right.
But an AI model absolutely needs labels to learn how to mathematically distinguish an angry customer from a happy one. That is a cognitive requirement. You are identifying the teaching material required for the digital brain you're trying to build.
So what happens if a team confuses this with described data and stops there?
If you stop at described data, you look at your files and say, great, we have 10,000 logs of customer chat, we have the text data, box checked, and you move on.
And then what?
Then months later in phase 4, you sit down to actually train the neural network and realize, wait a minute, none of these chat logs are labeled. The computer literally cannot learn the intent from this.
And now your project is completely stalled out.
You're worse than stalled. Yeah. You have to go all the way back to phase 2, hire a massive team of human annotators, and spend 2 unplanned months just labeling data. You missed the cognitive requirement early on, and it cost you everything.
So to contrast them cleanly for the listener to memorize, describe is static. It's the map. Explore is dynamic. It's checking if the soil can actually support the heavy house you want to build.
Perfectly said. Explore has 2 jobs. What is in the data and what the AI needs from it. It's the bridge between here is a file and here is intelligence.
That perfectly wraps up task group 1. Collect, describe, explore. Keep that strict sequence locked in your mind. Now we're moving on to task group 2. Data quality.
I cannot emphasize this enough. This is a critical priority group. If you fail this, you don't just fail the exam. In the real world, you probably get sued.
And notice, there's only one single task in this entire group. Verify data quality.
But do not let the fact that it's a single task fool you into thinking it's quick.
No, this is the gatekeeper.
It is the hard gate of the methodology. Nothing, and I mean absolutely nothing, moves forward to phase 3 data preparation until this gate is cleared. You do not prep bad data.
So let's look at a scenario I like to call the looks fine trap. This is a classic rookie mistake I've seen 100 times.
Oh man, I've seen this destroy so many expensive projects. It is probably the most common corner cut in the entire tech industry.
Let's see if our listeners can spot it. Scenario. The data team performs a visual inspection of a random sample. They look at 200 records out of a massive 500,000 record data set. They open it up in Excel. They scroll through a bit. They check a few random rows.
Just eyeballing it.
Yeah, eyeballing it.
Sure.
They say, yeah, it looks fine, and they move right on to preparation and training.
Famous last words in data science. Looks fine.
And at first, it seems fine. The model scores a 94% accuracy in training. Everyone is popping champagne in the office. But then, when it is finally deployed in production, the performance drops to a dismal 61%.
Which is basically useless.
Completely. A post-deployment investigation reveals that 30% of the full dataset actually has systematic coding errors that the visual sample completely missed.
Ouch. That is going to be a very painful post-mortem meeting with the executives.
Definitely.
Yep.
So the question is, what specific task was skipped here? Option A, describe data. Or option B, verify data quality.
Think about the difference between a sample and a verification.
Take a moment. The answer is B, verify data quality.
This scenario is the textbook definition of a data quality failure. Let's talk about the root cause here because it's important. Why did that 200 record sample fail them so badly?
Is it just a math problem? Is looking at 200 records out of 500,000 just statistically insignificant?
Well, it's not just the math. It's the entire intent and the methodology of the check. A visual sample, eyeballing it, only tells you that data simply exists and looks vaguely correct to a human eye on a screen.
Right.
Verification, on the other hand, is a formal, automated, programmatic process. It tells you if the data is trustworthy at a massive scale. Humans are just inherently terrible at spotting systematic anomalies in 500,000 rows. Scripts and automated checks are great at it. A sample tells you data exists. Verification tells you it's trustworthy.
The CPMAI source guide mentions the 4 dimensions of data quality that we need to actively verify. We should probably review those.
Yes. If you are taking the test, you need to know these 4 dimensions cold. They are completeness, accuracy, consistency, and timeliness. You have to check these formally, not just casually.
So in the scenario we just did, they had a systematic coding error across 30% of the data.
Exactly. That failure falls squarely under accuracy and consistency. If you don't run an automated script to check the full 500,000 row dataset for that specific error, a random sample of 200 might just happen to pull from the 70% that was clean, completely missing the massive pocket of bad data.
And the exam pattern here is really specific, right? I've noticed a very clear trend in the practice questions.
It is a massive red flag. If you see a scenario on the test that says a model performs incredibly well on training data but fails miserably on real-world inputs, your alarm bells should immediately ring and point to a missing verified data quality task.
But why is that? Why does it perform so well on the training data if the data is bad?
Because the model learned the bad data perfectly. It got a 94% on the test because the bad data was consistently bad. The AI just found the pattern in the garbage.
Oh, I see.
But when reality hits, when accurate, clean data finally comes in from the real world during production, the model cannot cope because it was trained to expect the garbage. It literally learned a lie.
That makes perfect sense. So, to contrast it with our earlier tasks, Explore finds the structure and the cognitive needs. Verify finds the actual problems.
That is the mantra. Explore tells you what you have. Verify tells you if what you have is broken.
I want to do one more quick challenge on data quality because it is so critical, and I want to talk about that consistency dimension you mentioned because I think it's the most subtle one to catch.
Let's do it. Consistency is the silent killer hiding inside the silent killer phase.
Let's call this the consistency gate scenario. A project manager assesses phase 2 completion for a new image recognition system. The collect, describe, and explore tasks are all marked done on the checklist.
Okay, doing well so far.
But the team proceeds directly to data preparation without a formal quality gate. Later, an investigation shows that the training data contained image records from a source system whose encoding scheme differed entirely from the others.
Oh, no.
Basically, incompatible file types were mixed in. Maybe some standard JPEGs mixed up with weird proprietary raw camera files that the model architecture literally cannot read.
The dreaded encoding scheme issue. A classic nightmare. You think you have a million training images, but half of them are digitally unreadable to your script.
So which task was skipped? Option A, explore data. Or option B, verify data quality.
Listen to what actually broke the system.
Take a moment. The answer is B, verify data quality.
Again, it all comes down to that word consistency. Consistency across source systems is a core, non-negotiable part of the data quality verify task.
Because described data might tell you, hey, we collected from system A and system B.
Exactly. But verify data quality goes a step further and asks, Wait, do System A and System B actually speak the exact same language?
Now, I can hear a listener asking a very logical question right now. Why wouldn't the Explore data task catch this? If I'm thoroughly exploring my data, wouldn't I naturally see the different file types?
You might stumble across it, sure, but you aren't actively looking for errors during exploration. You are looking for patterns and cognitive requirements. Exploration is about finding structure. Verification is about hunting for problems.
That's a huge difference in mindset.
It is. The encoding difference is a tangible problem. It is a suitability risk. If you don't run the explicit verification check, the poison just slides right in. And once that bad, incompatible data is baked into your prep pipeline, cleaning it out later is 10 times harder and more expensive than just blocking it at the gate.
So verified data quality is the bouncer at the nightclub. If you don't force him to check IDs at the door, the trouble gets inside.
Exactly. And once the trouble's inside the club, the party is basically over.
All right, let's move on to the final and honestly the most complex group. Task Group 3, Machine Learning Model Data Requirements.
Now we are fundamentally shifting gears. Up until now, we've been talking about the data as if it were just static files sitting on a hard drive.
Right, just spreadsheets and images.
Now, we have to start talking about the robot itself. What does the specific AI model need to actually function? This is where the exam heavily tests your knowledge of evaluation design and compliance.
There are 3 tasks in this group, and all of them are considered critical priority. We are going to hit all 3. First up, training and test data requirements.
This is critical because this is where you decide exactly how you're going to grade your own homework later on.
Let's do the challenge. I call this one the temporal leakage.
Sounds like a sci-fi movie.
It really does. Scenario. The team decides to defer their data split decisions, meaning how they plan to separate their training data from their testing data until they're actually doing the modeling in phase 4.
They kick the can down the road.
Exactly. They run the model, and the evaluation accuracy comes back at a staggering 91%.
Yeah.
Huge success, right? But then production collapses completely.
Of course it does.
A review shows that the test set they used to evaluate the model was actually drawn from the exact same time period as the training data.
Yep. The classic time travel crime.
So the question for the listener, which phase 2 task was completely missed? Option A, verify data quality. Or option B, training and test data requirements.
Don't let the high accuracy score trick you.
Take a moment. The answer is option B, training and test data requirements.
Let's spend some time talking about this concept of temporal leakage because it sounds super theoretical, but it is a massive practical problem in applied data science.
Can you unpack it for us? Why is this a strict requirement issue in phase 2 and not just, bad luck during the modeling phase?
Okay, imagine you are trying to build an AI to predict the stock market or maybe the weather. You have historical data stretching from January all the way to December.
Okay, a full year of data.
Right. If you just randomly pick days out of a hat from November to be in your test set, and you use days from December to be in your training set.
Wait, if December's in the training?
Then the model already knows what happens in December.
Oh.
So when you then ask it to predict the trends in November during your test, it's effectively just remembering the future trends that eventually led to the December data it already memorized.
Basically cheating.
It is entirely cheating. It literally has the answers to the test written on its hand. It is not predicting anything. It is just remembering.
So because it was evaluated on the same temporal distribution it trained on, the result is completely fake.
Same distribution in, inflated result out. That is your memory hook. You think you have a genius model with 91% accuracy, but you actually just built a cheat sheet.
So the training and test data requirements task is about setting up the strict rules of the game before you start so you don't accidentally let the AI cheat.
Correct. You have to lock down these evaluation rules in phase 2 before you even touch the algorithms. The study guide lists 4 very specific specs you must define here. First, the time range. Second, the split ratio, meaning how much data is for training versus testing, usually like an 80-20 or 70-30 split.
Right.
Third is temporal leakage control. That means explicitly stating you will cut the data by time, not just randomly. Like, we train strictly on January through October, and we only test on November and December. And finally, the minimum volume required for the test to be statistically valid.
If you don't do this specific task, you're basically walking into phase V with a blindfold on.
And the worst part is, you won't even know you failed until you deploy it and start losing real money in production.
Wow. Okay, next task in this machine learning group. This one is entirely about where the model physically lives. Let's call it the edge constraint.
Edge. For the listeners who might be new to the term, meaning on the edge of the network, we are talking about physical devices, security cameras, mobile phones, IoT sensors in a factory, not those big, limitless cloud servers.
Scenario. The project manager documents strict on-device storage limits for the system. Furthermore, the training data must rigorously cover 5 specific lighting configurations, dark, bright, shadows, whatever. And a very lightweight model architecture is required because the physical hardware is so small.
So we have physical limits and environmental constraints.
The question is this option A, training and test data requirements, or option B, edge model data needs?
Listen to the hardware limitations.
Take a moment. The answer is B, edge model data needs.
This one usually stands out to test takers because of the specific keywords. Things like on-device storage, lightweight architecture, or no internet connectivity.
But why does this need to be its own dedicated task? Why isn't this just lumped in as part of general training requirements?
Because the constraints here are entirely physical, not just mathematical. If my AI model lives in the cloud and it gets too big, I can just throw money at it and buy more server space. I can scale up infinitely.
Right, the cloud is essentially bottomless.
But if my model has to live on a tiny microchip inside a security camera, I have a very hard physical limit on how big the math can be. I have a hard limit on power consumption and memory. The memory hook here is, if the model can't reach the cloud, edge model data needs applies.
And the failure mode here has to be pretty painful.
Oh, it's devastating. Imagine you build this beautiful, massive, highly accurate model. It works perfectly on your developer laptop with its giant GPU.
Sounds great.
Then you try to physically shove that code onto the tiny camera chip and it just doesn't fit.
So what do?
Well, they panic, and they try to compress it. They start frantically chopping off parts of the neural network to make it smaller, and suddenly your accuracy completely collapses. Why? Because the data curation and the architecture were never co-designed.
You needed to know those physical limits way back in phase 2, so you could curate a highly specific, lean data set for a small model from day 1.
Right. Edge needs drive the data needs. If that security camera is going to be in an alley with terrible lighting, your training data absolutely must cover terrible lighting because that offline camera cannot just upload the image to the cloud for enhancement.
It's completely isolated.
You are on an island. You have to survive with exactly what you have on the device.
That makes a lot of sense. Okay, let's look at the very last task in this group. This is the third-party risk.
Yeah.
And honestly, this is huge right now in the industry. Everyone is downloading LLMs, using pre-trained models, grabbing open-source libraries off the internet.
Absolutely. It's the classic build versus buy decision. It is so much faster to buy or borrow an existing model, but it is infinitely riskier from a compliance standpoint.
Scenario. The team adopts a third-party model. Maybe it's an open-source sentiment analyzer they found on Hugging Face. They just grab it and go. Post-deployment, the legal team discovers that the open-source licensing strictly prohibits commercial use.
The corporate lawyers are going to absolutely love this one. That is a massive cease and desist letter just waiting to happen.
So what task was skipped?
Okay.
Option A, explore data. Or option B, pre-trained and third-party model usage.
Think about where the model came from.
Take a moment. The answer is B, pre-trained and third-party model usage.
This task is basically the due diligence phase of the AI world. The hook you want to remember is borrow a model, inherit its obligations.
Now, there are 3 specific components to this check in the guide, right? It's not just a matter of reading a licensed text file.
No, it is much deeper than that. You need to know these 3 components. First, fine-tuning data requirements. Meaning, do we need to provide new data to teach this borrowed model anything new to make it work for our specific use case?
Okay, that's one.
Second is provenance compliance. Does the original data that this third party used to train their model actually match our phase-I ethics and legal rules? Like, was it scraped legally from the internet?
Wow, so you're on the hook for how they trained it.
Yes. And third is cognitive capability coverage. Can this pre-built thing actually do what we need it to do, or are we just forcing a square peg into a round hole because it was free?
The scenario I read highlighted the licensing part of the risk, but that provenance part sounds really scary to me.
It is terrifying. If you casually use a model that was secretly trained on illegally scraped copyrighted data or data licensed exclusively for academic research only, and you stick that model into your company's commercial product,
your company's completely liable.
You are fully liable. Phase 2 is where you're supposed to check that tag. When you use an outside model, you are effectively laundering someone else's data decisions through your own project. You have to verify the source.
Here is the trickiest contrast I found when looking through the study notes. How do you clearly distinguish this task from explore data? Because they both talk about assessing cognitive capabilities.
It is a subtle distinction, but a very sharp one. Explore Data asks, does our internally collected data meet the cognitive needs of the project?
Okay.
Pre-trained and third-party asks, does this external model's built-in capability meet those needs?
Ah. So you have to look closely at the subject of the sentence. If the subject is the external model rather than your internal data, it's this task.
Exactly. If you are assessing a thing you are buying or borrowing from the outside, it is pre-trained and third-party model usage.
Wow. Okay, we have covered a massive amount of ground today. We've collected the data, described it, explored it. We've set up a hard gate to verify the quality.
And we've set the strict rules for the training splits, the edge cases, and the borrowed models.
That is the complete Phase 2 landscape. So now it is time for the final exam, the synthesis. I am going to give you a messy, real-world project status file, and you have to tell me exactly where the holes are.
All right, let's see if we can connect all these dots.
The final exam challenge. A project manager is reviewing the file for an AI insurance claims routing system. Here is the current status on his desk. Collect initial data is marked done. Describe data is marked done. Explore data, including all the claim category annotations, is marked done. And verify data quality, ensuring completeness and accuracy across all their source systems, is also marked done.
Sounds pretty robust so far. They really did their homework on the raw data side.
They did. However, looking closer, we find two issues. Gap A, there are absolutely no split ratios or temporal design rules documented anywhere.
Okay.
And Gap B, the team plans to use a third-party claims classification model as their base, but they have not assessed its licensing terms or its training data provenance.
I see the problem.
So the question for the listener, how many actual methodology gaps are there, and what exactly are they? Option A, one gap, which is verified data quality. Or option B, two gaps, which are training and test data requirements and the pre-trained and third-party model usage.
Think about the two specific things that were missing at the end.
Take a moment. This one is for all the marbles. The answer is B, two gaps. Both training and test data requirements and pre-trained and third-party model usage are missing.
Let's break this down really clearly. Why is it B?
Well, Gap A was no split ratios or temporal design. That is the literal definition of the training and test data requirements task. Without it, they are massively risking the temporal leakage we talked about earlier.
Correct. They're risking accidentally cheating on their own evaluation. And what about Gap B?
Gap B was third-party model was not assessed for licensing. That points directly and exclusively to pre-trained and third-party model usage.
Exactly. Now, importantly, did you notice what was not considered a gap in this scenario?
What do you think edge model data needs?
Right. Why wasn't that missing? The scenario was an insurance claims routing system. There was no mention of security cameras, no mention of offline mobile devices.
It's probably just running on a giant cloud server in the insurance company's back office.
Precisely. So that edge task wasn't missing. It just simply wasn't relevant to this specific project. You didn't fall for the trap of looking for something that didn't need to be there.
That's a great point. So the closing thought I want to leave everyone with here, we had two distinct gaps, but they were both inside the exact same task group machine learning model data requirements.
But they carry totally, fundamentally different risks to the business. And this is the profound takeaway for anyone taking this exam.
Right. Missing the training and test requirements collapses your math. Your evaluation accuracy is completely fake.
But missing the pre-trained and third-party check collapses your legal standing. You get sued, or your product gets shut down entirely for compliance violations.
Same task group, totally different risks. One destroys the algorithm, one destroys the company. That is exactly how Phase 2 tests you. It is not just about memorizing the names of the tasks. It's about deeply knowing what specific disaster each task is designed to prevent.
You know, Phase 2 is formally called data understanding, but really, if we're being honest, it should be called project survival.
Yeah.
Because if you respect these tasks and do them properly, you catch the silent killers before they ever get the chance to catch you.
That is perfectly said. And that brings us to the end of our Phase 2 simulation. Hopefully this deep dive gives you the exact framework you need to tackle these exam questions with absolute confidence.
Just keep thinking about the why. Don't just sit there and memorize the bulleted list. Think about the massive risk you are mitigating.
Thank you so much for joining us on the deep dive. Good luck with the prep, keep your eyes on the data, and we will see you when we tackle the next phase.